So now we can generalize this to the n-qubit Fourier transform. So let's recall this. Let's say J goes to summation e to the minus 2 pi I b sub n minus 1 to the n minus 1 plus dot 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 plus b0 times 1 b prime to the n minus 1 plus dot 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 plus b prime 0 times 1, all divided by 2 to the n. And we need to multiply this by k, where k equals 0 through n minus 1, and b primes are the bits of k, and b's are the bits of j. Now, well, we have the term, well, here we had the term J1 K0 and J0 K1. So those were term e to the minus 2 pi I b sub s b prime sub n minus s minus 1, all divided by 2 to the n. Is a Hadamard from b sub s, bit s sub j to b n minus s minus 1 of k. Because this is just e to the minus pi I. Oh, I forgot. There's a 2 to the n minus 1 here because there's a 2 to the s here and a 2 to the n minus s minus 1. So this is just e to the pi I bs b prime n minus s minus 1 over 2, which is just a minus 1 if they're both 1, and a 0 otherwise. So this is a Hadamard. So let's put that over here. So we start with b0, b1 through bn minus 1, and we need to Hadamard them all. And last time, actually, I called them J0 through Jn minus 1. Okay, I'm switching notation here, but so b prime 0 are b prime n minus 1, b prime n minus 2, all the way through b prime 0. And recall we did the smallest bit of j last and the largest bit of j first. So let's do the same thing here. Hadamard, 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 Hadamard. And let's call n equal 3, but just to make things more specific, b1, b0. And now we need to put in gates that do all these other transformations. So let's think about them carefully. We have bk and bj prime. No, Those are bad variables. E to the minus 2 pi I bs bt prime over 2 to the s, 2 to the t, over 2 to the n. That's just one term from here and one term from here. That's the gate, e to the minus 2 pi I bs b prime t 2 to the minus s minus t to the s plus t minus n, where all this is in the exponent despite my bad handwriting. There, that's better. Okay, so what does this gate do? Well, this gate is just 1, 1, 1, e to the minus 2 pi I 2 to the s plus t minus n. And we can assume s plus t is less than n minus 1. Assume s plus t is less than n minus 1. Why is that? Well, if s plus t was equal to n minus 1, then it comes from this term, which transforms into a Hadamard gate in our circuit. So if s plus t is less than n minus 1, you get a different gate. So what does that do up here? Well, if s plus t is less than n minus 1, you have, well, if s, so this is s, and here is t, and s plus t is less than 3, then there is room here for a gate after you do this Hadamard and before you do that Hadamard. And of course, it doesn't matter where exactly you put it, as long as you put that gate between bi and bj prime, or bs and b prime t, after the Hadamard gate on t and before the Hadamard gate on s. And what gate should we do? Well, let's call this R. Okay, I want to use a notation in the book. So we'll say R sub k is equal to 1, 0, 0. E to the minus 2 pi I over 2 to the k. And maybe I should just put the gates in now and then explain exactly why I put them in. And so here, I'm going to put an R2 here, an R3 here, and an R4 here. Okay. And now I want to put an R2 here and an R3 here. And now I want to put an R2 here. And so can everyone read this? So I've put an R2 between all adjacent qubits, and R3 between all all pairs of qubits which are 2 away, and R4 between all pairs of qubits which are 3 away from each other. And generally, I'll put an RT between all pairs of qubits which are t plus 1 away. And R sub I is just this gate, 1, 0, 0, e to the minus 2 pi I over 2 to the k. So this is a controlled R sub I. So why did I do this? Well, this R2 comes in between, for example, B3. This is right. OK. So this is B0. And here it's interacting with B1. And 0 plus n minus 0 plus 1 is 3. So you want an R sub 3 because what this depends on is n minus s minus t. So here we have a B0 on the right. So that B0 prime on the right interacting with a B1. And it's B1 because it's before this Hadamard gate that turns B1 into B2 prime, and it's B0 prime if it's after this Hadamard gate that turns B3 into B0 prime. So the gate you want depends on n minus 1 minus 0. And that's, in this case, 3. But you can see, because these are going down and these are going up, the sum of this value t and that value s over there just depends on the distance between the wires. And the distance between the wires, it works out. You have an R2 between adjacent wires, an R3 between pairs of wires that are 2 away, and R4 between pairs that are 3 away, etc. So this circuit does a 4-qubit Fourier transform. And of course, at the very end, you have to swap them to get the bits in the right order.